Sabinsky reaction. Okay, so first thing, goggles first, apron, and because this has skin irritants, always wear gloves. Okay, so we are going to be mixing 4 solutions. We have a potassium bromide solution, and each of these we need 150 milliliters, except for the Fairwine because it's the indicator. So, that's the 150 milliliters of the potassium bromide solution. Oh wait, we're actually using 250 for our actual reaction, but this one we're scaling it down to 3/5 of the actual amount. So this one is a malonic acid and potassium bromide solution, and again we need 150 milliliters. So there's that. And then we have another 150 milliliters of a cerium 4 ammonium nitrate and sulfuric acid solution. As you can see, it's yellow from the cerium 4, just if you were wondering. And then you only need 9 milliliters of the Fairwine solution, because it's an indicator and you don't need as much of it. Okay. And there's the Fairwine. So now that we have everything all measured up, now we're ready to start the reaction.
Alright, so before we begin the reaction, there's a couple things I want to cover. So one, because some of the chemicals will react to produce bromine gas, which is toxic to inhale, you should be doing this experiment in a fume hood, and it'll suck all the toxic fumes up and out of the building. And also you need a magnetic stir and a large beaker that you can mix everything in.
There are the solutions.
Now about the BZ reaction, it's basically one big redox reaction made up of 4 steps. So just to go over reduction reactions, reduction is when something gains electrons, and oxidation is when it loses electrons. One of the processes, I've written the half reactions here on the board. Okay. So here you have bromate ions going to bromide, and then you have bromide ions going to bromine. So because a lot of our substances are acids, we're going to balance these based on an acidic solution. So first I'm going to do oxidation states. Now how you do this is each element is assigned its own number. Oxygen is always -2. So here we have -6, and since it has a -1 charge, bromine has to be +5. And then always in its elemental state, element will have an oxidation state of 0. And these are both 0. Now here the oxidation state is already written because it's in its ion form by itself. So this is just -1. So we'll start with the top reaction. In order to get from +5 to 0, this needs to gain a negative charge. Specifically, it needs to gain 5 electrons. And that'll balance the +5 charge. And because we only have 1 bromine on this side and 2 on this side, we're going to say, okay, the charge on the left is still not balanced because we have -5 and -1. So on total, this is -6 on this side, and you have 0, it's neutral on this side. So because we're in an acidic solution, there's a surplus of hydrogen ions, or H+. So in order to balance it, we're going to add 6 positive charges to this side. Sorry, my marker is not functioning. Okay, And you can't just leave hydrogens on one side and not on the other. So in order to balance the hydrogens, we're going to form water on this side. So we have 3 oxygens and 6 hydrogens, which is perfect for 3 water molecules. And here's your balanced first half reaction. Now, if the top half reaction gains electrons and is reduced, the bottom has to be oxidized. So it's going to lose electrons to become neutral. In total, it's going to lose 1 electron. We put it on the right. And again, we need to balance the bromines. Since there are 2 on this side and 1 on this side, we're going to say 1/2. And since we have a -1 charge on both sides and the bromines are balanced, this half reaction is done. But before you can combine them, you need to balance the number of electrons of both. So this one, you have to multiply by 5. And then you just add. And voila, you have a balanced redox reaction. So first we do is we have to react both the bromide and the malonic acid solutions in the beaker. Can you turn it on? Yep. So we add those 2 solutions together. And nothing happens. Isn't that exciting? There is. That first chemical reaction I wrote on the board is occurring right now, as the bromate is both oxidized and reduced. Okay. Now, we're going to add C and D. C first. As you can see, the color of the solution changed from a light yellow to a dark red, or dark orange, actually. And here's the indicator. It'll stay cloudy and mucky green for a
it's like a green.
Yeah, it's not a very attractive color.
What? So right now, the reaction is occurring where cerium is being oxidized and reduced between Ce4 plus and Ce3 plus. Alright, so now, as you can see, something's happening, and it's turning green. And green indicates that the yellow Ce4 ions, cerium 4 ions, are oxidizing the iron in the ferroin indicator. The iron 2 is a red color, but the iron 3 ions are blue. So what it's doing is it's oxidizing the iron 2 ions to become iron 3 ions, and that'll turn the solution blue. And the transition, because of the yellow cerium, will be green, which is how you get the green that came before. Right. And that'll become blue. And so now we're going to violet, and this is when the Ce3 plus is reducing the blue Fe or iron 3 plus, and it's going to become the red Fe2 plus. But the stage between the blue and the red colors creates the violet that you saw. Yes, and it will get to a better red than this. It's a little slow at times. This whole, oh, there we go.
Now
and see, it went through the blue transition stage, which
now we're
was
back at green.
Yeah. So this whole reaction is based on the concentration of bromide ions. There are 2 processes, process A and process B. Process A occurs or dominates when the bromide ion concentration rises above a certain point. And then what occurs in process A is the consumption of those bromide ions, and as enough are consumed and the concentration decreases enough, then process B will dominate.
In process B, this bromate ions are being reduced into bromide ions from +5 to -1, and this allows for the oxidation of Ce3 plus to cerium 4 plus.
Turn this up a little bit.
Cerium 4 plus, which produces the red color of the solution.
orange, yellow, green, blue, purple, pink. Red, orange, yellow, green, blue, purple, pink. It's a rainbow, it's a rainbow, a beautiful rainbow in the sky. It's a rainbow, it's a rainbow, a beautiful rainbow in the sky. Red, orange, yellow, green, blue, purple, pink. Red, orange, yellow, green, blue, purple, pink. Red, orange, yellow, green, blue, purple, pink. It's a rainbow, it's a rainbow, a beautiful rainbow in the sky. It's a rainbow, it's a rainbow.
Okay, so when you're done with this reaction, you can't, because of the strong acids, you can't just pour it down the drain. You need to neutralize it. What we took is sodium carbonate, and it'll basically mix with the extra H plus in the solution, and it'll form water and carbon dioxide, which you'll see right here. And you can see the kind of gas being released from it, and it's fizzing. You know you've neutralized it when it's not fizzing anymore. Okay, that's perfect. If only it would freaking stand.
Wait, I need my gloves.
Kelly does not have her gloves on.
Did you want me touching your camera with these things? There's like Fairway all over it.
Yeah. To make it a little more colorful.
Right now it is, but we're gonna